Now we can begin to answer this question of what is the effect of selling more and more chairs on this ratio? Well, let's take a look at this guy graphically. Now if you notice in terms of vertical asymptotes, since this will only equal 0 when n is a negative number, so meaning to say that the only way you can make this equal to 0 is if you take a positive number and add a negative number to it. So this means that n would have to be negative. So we're going to ignore the vertical asymptote for this problem. We're going to focus just on graphing the horizontal. So let's just take a look at a couple of examples of what happens to this ratio and what this ratio might mean. So let's take a look at a table of values to see what's going to happen as the value of the number of chairs increases. Well, here I have my function, my y equals. Again, we want to make sure that plot 1, plot 2, plot 3 are all unhighlighted, which they are, so that's good. And I'm going to go to second window, and I'm going to adjust my table. So let's start our table at 0 chairs. We're going to see, first of all, what would happen to this ratio if we had 0 chairs. And then we'll increase the number of tables at 100 unit increments. So I'm going to go over to my table, second graph, and I notice that here's what's happening to this ratio. So what does this actually mean? If I sell 0 chairs, well, let's come back to the function for a second. I'll have a ratio of 1.19, or just about. So let's think about what that means. So R of 0 would be 29,500 plus 99 times 0 divided by 24,800 plus 64 times 0. So that these terms would go away, and I'd be left with 29,500 divided by 24,800. Let's think about what these units represent. This is dollars, and this is dollars of revenue. And this down here is dollars of cost. So my ratio is dollars of revenue per dollar of cost. Well, that's what I'm actually getting when I divide those. I get about 1.19, oops, I'm not going to put that there, 1.19 dollars of revenue for every dollar of cost. So if I'm producing that many chairs, then I'm going to gain a dollar. If I spend a dollar, in costs, I should earn $1.19 in revenues. So what does that mean? Well, that means my profit is going to be 19 cents on every dollar that I spend. So we get $1.19 for every dollar we spend. So we really earn 19 cents. So what's happening to that ratio? Well, if this number represents dollars of revenue per dollars of cost, look what's happening here. If I only sell 0 units, I get $1.19 in revenue. But as I sell more chairs, I notice that down here at 600, I get $1.41 in revenue for every dollar of cost. So that's a good thing, right? Because our revenue is going up. Now, how far is it going to go up? Well, we can kind of see it slowing down. It's not going up quite as much. It's only going up by a penny every several thousand units. And what I'm going to do is I'm going to come down to my table, my table setup, and I'm going to still start my table at 0, but I'm going to go up in increments of 1,000 to see kind of what the stabilization point is. And I'll come back to my table, and I'll notice that, wow, it really seems to be pretty stable around $1.54 or so, $1.55 maybe. So what's the stable point? Well, we know this. We know that if the order is the same in the top and the bottom, the highest exponent on the variables is equal, then the ratio of their coefficients will represent the horizontal asymptote. So 99 divided by 64, if we calculate that, 99 divided by 64, we'll get approximately about $1.55. So we get, so notice that in our table that's pretty consistent because we are still about 1.54, and you'll notice that is really beginning to increase slowly, and so that is equal to about $1.55 per dollar of cost. So $1.55 earned in revenue per dollar of cost. So we can continue to produce infinitely many units, but guess what? Our revenue, or our ratio as a function of the number of chairs we sell, is going to look a lot like this. And we're going to, again,